So in the last week, we introduced the concept of an inner product space. We defined the notion of length of a given vector in an inner product space, and we also defined what it means to say that two vectors are orthogonal to each other. We talked about a few properties of orthogonality. So for example, we proved that if W is orthogonal to vectors v1, v2 up to say vk, then W is also orthogonal to a linear combination of these vectors. And we proved the Pythagoras theorem in an inner product space. We also generalized it to finitely many vectors. So in this week, we will begin by discussing the notion of an orthonormal basis. It is a basis, basically it's a basis which consists of vectors which are orthogonal to each other and each of which has length 1. So let's begin by discussing what it means to say that a collection of vectors. So we say that a collection of vectors v1 to vn in an inner product space V is orthogonal when it is orthogonal pairwise. If the inner product of Vi with Vj is equal to 0 whenever I is not equal to j. And we say that a collection is orthonormal if it is not just orthogonal but also if the length of each of the vectors is 1, if it is of unit length. So we say that the collection is orthonormal. It's normalized, and that is where the normal is coming from. It is orthonormal if it is orthogonal and if the length of Vi is equal to 1 for every I. So it's not just enough for the vectors to be orthogonal, pairwise orthogonal, but the length of the vector should also be 1. So let's look at a few examples. So example, let's work with R2 or maybe R3 with the standard inner product, which is the dot product. So consider R2 with the standard inner product and consider the collection of vectors. So let's see, v1 let it be equal to 1 2 0 and v2 be equal to 0 0 3. Then this is an orthogonal set of vectors, this collection. Then this collection of vectors is orthogonal. That's a straightforward check. If you look at the inner product of v1 and v2, that will just turn out to be 0. However, if you observe carefully, this is not an orthonormal collection. However, this is not an orthonormal collection. What would be an orthonormal collection? Let's see. Maybe so v1 equal to 1 by square root of phi, 2 by square root of phi 0, and v2 equal to 0 0 1 by root 3. Or maybe not, just 1. This is an orthonormal collection. This So if you look at this collection, is an orthonormal collection. If you look at the length of V1, that's just going to be square root of 1 by 5 plus 4 by 5 plus 0, which is square root of 1, which is 1. So this is an orthonormal collection of vectors. So why are we considering such collections? Of course, there are many good properties which come out, but let's see. Orthonormal properties are, orthonormal collection of orthonormal vectors have some really nice properties. One of which is that it is linearly independent. So let's prove it. Let's state the proposition. If V1 to Vn is a collection of orthonormal vectors, then they are linearly independent. They are linearly independent. Well, let's have a look at a proof. Well, we could prove it in multiple ways, but let's make use of what we already know. We have already proved. So suppose we have a linear combination of V1 to Vn which is equal to 0. Suppose A1 V1 plus A2 V2 plus An Vn is equal to the 0 vector. So as you can see, I have slowly again stopped indicating whether it is a complex vector space or a real vector space, or rather a complex inner product space or a real inner product space. But unless and until it is mentioned explicitly, all our results go through for both. So let me not unnecessarily bring it up again and again. Our results, whichever we are stating and proving, are true for inner product spaces over both real numbers or inner product spaces over complex numbers. Alright, so suppose we have a linear combination which is equal to 0. Then let's see what is the inner product of A1 V1, or maybe let's use the corollary to the generalized Pythagoras theorem. By corollary to the generalized Pythagoras theorem from the last week, what can we conclude? Can conclude that the length of this vector, the length of A1 V1 plus up to An Vn square, this is going to be equal to mod A1 square length of V1 square plus up to mod An square length of Vn square. But what do we know about V1, V2 up to Vn? It's, after all, as you can see, let me underline it, it's a collection of orthonormal vectors. So in particular, each of these Vi's have length 1. That means this is just equal to mod A1 square plus mod A2 square plus mod An square. So till now we didn't have to worry about which field of scalars we were working on, but again, irrespective of whether we are working in an inner product space over complex numbers, or whether it is an inner product space over real numbers, the absolute value, the square of the absolute values are all positive numbers. So this is all a sum of, so this is greater than or equal to 0. When is the equality going to come up? With equality only if mod ai is equal to 0 for all I. So this will happen only if each of these positive numbers are 0. Even if one of them is non-zero, it will be strictly greater than 0, and therefore it cannot be equal to 0. So it is 0 means that each of them is forced to be 0. But when is the absolute value of a real number or a complex number equal to 0? This happens only if the number itself is 0, only if the scalar itself is 0. So this is if and only if ai is equal to 0 for I equal to 1 to n. And this forces our vectors v1, v2 up to vn to be linearly independent. So just to tell you or show you that the operation of inner products and the various consequences are powerful, let's look at an alternate proof, which is, it's not like this, it's not elegant, it's just that we can see that there are multiple approaches. So suppose again a1 v1 plus up to an vn, let this be equal to the 0 vector. Then if you look at the inner product of a1 v1 plus up to an vn, and let's look at the inner product of this with vj, where vj is one of the vectors from the collection. By linearity, this is just going to be a1 times inner product of v1 vj plus a2 times inner product of v1 vj plus an times the inner product of vn vj. Now what do we know about vi's? They are orthonormal. That means if I is not equal to j, inner product of vi and vj will be 0, and if I is equal to j, the inner product of vj will be the square of the length of vj, which is equal to 1. So this is just going to be equal to aj times the inner product of vj with vj, which is equal to aj, because length of vj is equal to 1, and therefore inner product of vj with itself is equal to 1. All other terms vanish, notice that. But what is a1 v1 plus a2 v2 up to an vn? It's just the 0 vector. So this implies 0. So this is equal to 0, right? So this implies 0 is equal to aj. And if you do it for j equal to 1, 2, 3 up to n, we conclude that each of the aj's are forced to be 0. And hence v1 to vn are linearly independent. Alright, so we gave 2 proofs for this result, but nevertheless it's a good result to keep in mind, and this is just the beginning of many good things that we get out of orthonormal set of vectors. Let's next define what is meant by an orthonormal basis. As you can guess, an orthonormal basis is a basis which is also an orthonormal collection. So, definition of an orthonormal basis. So, let me just write definition here. An orthonormal basis is a collection of vectors, which is both an ordered basis and an orthonormal set, which is an ordered basis which is an orthonormal set, which is orthonormal. Let's look at a few examples. So the standard basis in Rn of Rn, this is an orthonormal basis with respect to the standard inner product in Rn. This is an orthonormal basis. It's a check for you to see that they are orthogonal to each other and that each of them has unit length. It's an orthonormal basis with respect to the standard inner product. Let's usually work with standard inner product. So if I fail to mention which inner product we are working with in Rn, it will be the standard inner product. Okay, let's be a little more adventurous. So another example. So let's look at the following collection. So let V1 be equal to 3 by 5 and then 4 by 5. You can check that the length of V1 is 1. And what about V2? V2 be minus of 4 by 5 and 3 by 5. You can check that V2 has also length 1. And it is immediate to see that in R2, V1 and V2 they form an orthogonal collection, they form an orthonormal set and therefore it is linearly independent. Dimension of R2 is 2 and any linearly independent set of size 2 is a basis. So this is an orthonormal basis. Okay, so orthonormal bases are quite handy to work with. So if, for example, if you start with an arbitrary basis in say Rn and if you would like to, so we know that every vector can be written as a unique linear combination of vectors in this ordered basis. If we are to write down explicitly what this linear combination is, it's a very tedious process. In fact, even in small, in low dimensional Rn, so for example R4 if you take, and if you want to write say 1, 5, 6, 7 in terms of a basis which is not the standard basis, it's quite complicated to find out what the coefficients are. And that is precisely where orthonormal basis comes in a very handy manner. We can write down explicitly what would be the coefficients featuring in the linear combination of the given vector. In a very simple manner we can do that. So that will be our next goal. So let me just note what I just said. So in vector space with a basis, with an ordered basis given by say V1 to Vn, we can write a vector and write V. So given V in capital V, we can write V as being equal to A1 V1 plus up to An Vn, where Ai's are scalars. Uniquely we can write that. We can write in a unique manner V as this particular linear combination. However, it's very difficult. It's usually difficult to compute AI explicitly. Even in small vector spaces or in vector spaces like R3, R4 itself, it's in R2 I wouldn't say it's very difficult, but in R2, R3, R4 itself it starts becoming quite tedious. So in order to capture what I said a few minutes back, let me state it down as a proposition. So let V be an inner product space and suppose beta equal to V1 to Vn be an orthonormal basis and let V be a vector in capital V. Then V is equal to A1 V1 plus up to AN Vn, where AI is just the inner product of V with Vi. So we know explicitly what the coefficients of each of Vi's are in the linear combination of V1 to Vn, which is equal to V. So let's give a proof of this proposition. So suppose, if V is equal to A1 V1 plus up to AN Vn, suppose this is the case, and let's look at what is the inner product of V with say Vi. Then inner product of V with Vi will just be the inner product of A1 V1 plus up to AN Vn, inner product of that with Vi. But what is this? This is equal to A1 times inner product of V1 with Vi plus A2 times the inner product of V2 with Vi plus up to AN times the inner product of Vn with Vi. But again, beta is an orthonormal basis. So inner product of Vi with Vj is 0 if I is not equal to j. So this is just going to be equal to, we have already used this trick once before. So to illustrate the power of it, I had given the alternate proof earlier, and this is just ai times the length of Vi square, which is 1, and therefore this is equal to ai, and that's precisely what we had set out to prove. So this makes a lot of things quite simple for us. So for example, if V is some vector, so let me just say that we have proved it. So suppose V is in capital V, and then we are interested in what is the column vector of representation of V with respect to beta. Then this is just equal to the column vector which is given by the inner product of V with V1, V with V2, and so on, V with Vn. So we now have an explicit column vector representation of V with respect to beta. Even better, suppose, so if T from V to W be a linear transformation, this also makes computing the matrix of T easier if W is an inner product space, where V and W are vector spaces over F transformation, and suppose beta gamma be ordered basis of V and W respectively. Suppose further that gamma is an orthonormal basis. Then if you notice what T beta gamma is, I'll just write it as this. This is just going to be T V1 gamma T Vn gamma, where beta is equal to V1 to Vn is the ordered basis of V. So we have written the column vector representation of each of T V1, T V2 up to T Vn, and that will be the columns of our matrix. Alright, so let's now look at a few examples of what we just did. So we have proved that given an inner product space and given an orthonormal basis, if we have any vector V if we have a linear combination of V1 to V1, Vn giving vectors in V, then we know exactly what that linear combination is. So in particular in R2, if beta is just say 1 0 and 0 1, here we don't really need to do this exercise because it's quite straightforward already. If if v is equal to say x comma y, then inner product of v with, let's call this v1 and let's call this v1 is 1 0 and v2 is 0 1. V with v1 will just be the inner product of x y and 1 0, which is equal to x, and similarly v with v, let me write v1 very carefully, v2 here, this is just going to be similarly y, and therefore we know that this is, therefore v is equal to x times v1 plus y times v2, which we knew. So maybe I shouldn't have written v1 v2, it's the standard basis, and I think we had given e1 e2 as the notation for it, but that's okay. And let's look at something which is more complicated. This was quite straightforward. So let's look at another example where say beta prime is something like 3 by 5, 4 by 5, like we were considering earlier. This vector, so let's call it some names. So this is v1 and v2 is minus of 4 by 5 and 3 by 5. So let's take the simplest vector 1 comma 0, which we can consider. Let v be equal to 1 comma 0, and we would like to write v as a linear combination of v1 and v2. This itself we have slightly increased the complication, because you will now have to write down a linear set of linear equations and solve for them to get hold of what the coefficients would be. But now we have a tool. We know that the coefficients will just turn out to be v. So let me write a to be equal to, what is v1? Let's calculate it explicitly. What is this? This is just 1 0 inner product of 1 0 with 3 by 5, 4 by 5, which is equal to 3 by 5. And how about the inner product of v with v2? It will just turn out to be equal, let me not write too much, it's just minus of 4 by 5, and therefore we know. Therefore, by what we just did, this is equal to 3 by 5 times 3 by 5 comma 4 by 5 minus 4 by 5 times minus of 4 by 5 3 by 5, and you can check that this is actually the case. So without going down to solving a set of linear equations, this is making our life much easier. It only gets better actually with higher the dimension, the complexity starts coming down accordingly. Let's now look at one more example which is of great importance in general to both the mathematical community and others. So even in engineering, this example is of great interest. So let's consider the vector space. Let V be the vector space C01C. And let's consider a collection of vectors. So this example, let me just put here the name as Fourier series. This is a standard a course in Fourier analysis is there in graduate studies. So because of the vastness of the subject, so this is just skimming over the tip of the iceberg, but nevertheless it's a good place to give an example. So let's consider the vector space. If you recall, C01 to C is the vector space of all continuous functions from 0 1, complex valued continuous functions. And let's consider the following collection of vectors. Let's consider the collection of vectors. Collection of vectors V1 to be say Vk. Let me put it as Vk. This is just e to the power 2 pi I k x. So Vk is a function, remember. So this is Vk of x is defined to be e to the power 2 pi I k x. And this is being done for each integer. So not just positive numbers, not just natural numbers. For k equal to 0, for k equal to minus 6, minus 10, for all such integers, we are defining Vk of x to be e to the power 2 pi I kx. So let's see what is the what are the properties of this this collection of vectors Vk of x. So and what is the inner product? Okay, so let us consider the inner product. So before I mentioned the inner product, if I had given Vk, it doesn't really make sense. Inner product, of course, it makes sense, but why these functions? That will not be justified. The inner product is given by f comma g. The inner product of this is already defined once in the previous week. This is just the integral of f g bar. So let's see what happens to our vk's. So if you look at vk for any k, this is just going to be integral of vk of x bar. So this is e to the power 2 pi I x times e to the power 2 pi I kx, from 0 to 1 and e to the power 2 pi I kx bar dx. This is exactly what our integral will be. But then what is the bar? If you go back and set, this is just cos 2 pi I kx plus I times 2 pi I kx, which will turn out to be, so this is just, I'll leave it to you to check that this is integral 0 to 1 e to the power 2 pi I kx times e to the power minus 2 pi I kx dx. And this will be e to the power 2 pi I kx minus 2 pi I kx dx, which is e to the power 0, which is integral of 1 dx, where the limits are from 0 to 1, which will just turn out to be 1. So length of vk square is equal to 1. So this is already a unit vector, it's normalized. This is a normalized vector. Okay, how about the inner product of vk with vj? So let's look at what is vk inner product with vj for j not equal to k. So for j not equal to k, let's look at what this is. This is just inner product integral from 0 to 1 e to the power 2 pi I kx. Let me jump a few steps and directly write as e to the power 2 pi I minus of e to the power 2 pi I jx. So notice that the I featuring in the exponent here is the square root of minus 1 and it is not an index. However, k and j are indices. So this is equal to integral 0 to 1 e to the power 2 pi I times k minus j times x dx. And this is just e to the power 2 pi I k minus j x by 2 pi I times k minus j from 0 to 1. This is exactly what the integral will turn out to be. And you can check that this is just 1 minus 1 by 2 pi I k minus j, which is equal to 0. The first one coming because e to the power 2 pi I times any integer is 1 and e to the power 0 is also 1. So the second one is from e to the power 0 and this is equal to 0. So what we have established, let me just go back and show what we just proved. We showed that the inner product of vk with itself is 1 and the inner product of vk with vj is 0 for all k not equal to j. So hence the collection of vk, or let me put it this way, v minus 3, v minus 2, v minus 1, v0, v1 dot dot dot. This is an infinite collection of orthonormal vectors. So we will not talk about Fourier series right now, because that is beyond the scope of this course. We will have to develop convergence of an infinite series and such things. But rather what we will do is, let's look at a specific subspace. So define Tn to be the span of V0, V1 up to Vn. So these are called the trigonometric polynomials, called the trigonometric polynomials. So what will be a typical element here? So any element here, so a typical element f will be of the type a1 a0 v0 plus a1 v1 plus up to an vn. And if you write it down, this is just a0 plus a1 times e to the power 2 pi I x plus a2 times e to the power 2 pi I into 2x and up to an e to the power 2 pi I nx. So this is something like a polynomial, right? So a0 plus a1x, a1 times say t plus a2 times t square and so on. Right, so that is why it's called trigonometric polynomials. So let's now implement whatever we have just developed to an arbitrary element in Tn. So then for f inner product with Vk, this is just going to give you the, by whatever we just developed, this is our Ak, right? But what is f inner product with Vk? This is inner product of f with e to the power 2 pi I k x dx. So I should be a little more careful. This is 0 to 1 f of x e to the power 2 pi I minus e to the power minus 2 pi I k x dx. These are called the Fourier coefficients of f. Are called the Fourier coefficients of f. And we also have the famous formula which says that if you look at the length of norm f square is equal to summation mod ai square. This, if you write down with ai is now known explicitly. If you write it down like this, this is called the Plancherel formula. Alright, so in the next video we will discuss orthogonality in much greater detail by talking about when two vector subspaces can be orthogonal to each other.